Thanks, and thanks everyone for being here today. And also thanks to Sasha and all the audio analytics people who invited me here today to give this talk and for this nice series of sound recognition tech talks. So today I'm going to talk to you about machine listening and for audio analysis technologies, but with a specific angle, which is this angle on matrix decomposition or matrix factorization techniques that are quite popular, have been quite popular for the past 10 years or so in the field. Before going into the meat of the talk, I will just talk briefly about where I come from, the Center for Digital Music, going to briefly discuss the main problems in machine listening, and then dive into matrix factorization methods and how they can be applied to both music recordings, but also to acoustic scenes, or basically everyday sounds. So where I come from, the Center for Digital Music is a group that was formed in 2003, for which its main focus is digital technologies for music and audio. It has over 70, I think, members, and we have organized quite a few conferences in the past years. And you might be familiar with software that we have developed, like Sonic Visualizer, which is a popular tool for sound visualization and feature extraction. I think it has over 200,000 downloads. This figure here shows the basic areas of research that we're working on. It's pretty interdisciplinary. I'm more or less situated in this part here, somewhere between machine listening and music informatics, but there are also other people working in other topics like computational creativity, systems that can compose music, the mathematics of music, analysis of performance, human-computer interaction for music, new instruments, audio engineering for example, for sound production. On funding, currently C4DM has a large EPSRC grant which is on fusing both audio technologies with semantic web technologies, also a platform grant, and the Center for Doctoral Training in Media and Arts Sound Technology. And here are just a few of the industrial partners that have been working with C4DM over the years. Perhaps of particular note is that C4DM was one of the founding partners of the BBC Audio Research Partnership, which still continues to this day. And on to the main part of the talk, machine listening. In other words, audio analysis. In the US, people call it computer audition or computational audition. In a nutshell, it's about extracting meaningful information from audio signals. The types of sounds that machine listening technologies can be applied to can be pretty much everything: speech, music, or environmental or everyday sounds. You might encounter these as non-speech, non-music sounds or acoustic scenes. Still, there's no predefined terminology about this. And machine listening really combines two main disciplines, so that's of signal processing and machine learning, but also has elements of other disciplines like acoustics, perception and cognition, and also for specific problems, linguistics or musicology, or even bioacoustics, biology. As far as music audio is concerned, the core problems in the machine listening field are, first of all, on tonality, to detect notes, multi-pitch detection, multiple concurrent notes, to extract chord or key information. On the rhythmic aspect, to detect onsets, so when a musical note might start or finish. Beat tracking, to detect beat information or to infer meter. And also on source separation, so if we have a music signal, can we extract individual instrument tracks from there, or can we identify the specific instrument sources that are present in the signal? And as far as applications are concerned, machine listening for music recordings can be used for music information retrieval purposes. So to organize, navigate through music collections, can be used for interactive systems, like for automatic accompaniment. Computer music can be used as an aid for new compositions, musicology. This figure here shows one of the core applications in machine listening for music, which is automatic transcription. Can we create a system that can convert an audio recording into music notation automatically? That's a bit tricky and hasn't been fully solved yet. So on the other aspect of everyday sounds, or acoustic scenes, I would identify three core problems. Firstly, sound recognition, and maybe some more focused problems like sound event detection, or acoustic event detection as it's also called, which is about detecting the start and end times and the identities of specific events within an audio recording. Here in this figure, there's a few events like from an office environment, like phones, door knocks, door slams, people clearing the throats and things like that. Another application is acoustic scene recognition, or characterization or identification, which is about systems that can automatically recognize the acoustic environment that this audio recording is placed in. Is this an office? Is it a park? Is it a street? And finally, source separation. So if we manage to identify some events, can we maybe separate them from the rest of this complex audio recording? And there are quite a few applications. I'm sure that Sasha and the audio analytics people can find more applications in this, but I would say mainly audio archiving, security and surveillance, smart homes and smart cities, urban planning, maybe another application, acoustic ecology, so for example in biodiversity assessment automatically, and many more, I'm sure. And now, how does this all fit within this matrix factorization paradigm? Non-negative matrix factorization was a technique that was originally proposed in 1999 by Lin Tsung, and it was originally focused on the fields of image processing. They came up with this method which could, in a non-supervised manner, take as input a non-negative matrix and decompose it as a product of two other non-negative matrices. So the constraint that had was basically that the data that was used both as input and as output were non-negative. They were interested in that because they were working on topics like face recognition, and they had this concept that basically an image is the sum of its parts. So if we have an input face here, this is from the original paper, by the way, it can be approximated by the sum of its parts. So a nose, two eyes, eyebrows, etc. And the idea was that if we have as input this image of a face here, NMF can produce two sets of matrices. One, which is called the basis matrix, which basically has information about the specific parts of that image. You might see a mouth here, eyebrows there, and things like that. And the other matrix, which is called the encoding matrix, will have weights saying that this face can be created as a linear combination of these basic parts of the face with a certain set of weights. So that was the basic concept. And NMF, as it is, stands squarely somewhere between machine learning, signal processing, and mathematics, with quite a few applications, for example, dimensionality reduction, clustering, classification, denoising. If we put a bit more math into it, the idea is that if you have a non-negative matrix V as input, the goal is to find two non-negative matrices, W and H, which can approximate as a product the original matrix V. And the key concept here is that the rank of this factorization, so this R here in the dimensions of W and H, if it is small, then it can lead to a compression of the original data. So it can actually lead to maybe a meaningful solution, a meaningful factorization. Over the years, various algorithms have been proposed to address this topic. Of how can we actually estimate these two matrices W and H. W is the basis matrix I told you before, so the parts maybe of the face, and H is this encoding matrix, the weights of the basis that can produce the original image. Algorithms like expectation maximization, gradient descent, alternating least squares have been proposed, and also different cost functions have been used. A cost function is basically like a criterion in order to come up with this decomposition, which minimizes the distance between the inputs and the output of the algorithm. Cost functions like the Euclidean distance have been used, or the Kullback-Leibler divergence. Then, in 2003, Paris Smaragdes and Judith Brown had this idea. What if we apply NMF in a magnitude spectrogram of an audio recording? Here, this figure shows a magnitude spectrogram for a short music segment. I'm going to play that now. So what you see here is, this is a two-dimensional representation, frequency over time. And here you can see the start and end times of a few notes that you just heard now. What's also interesting is that you see basically that this line in the bottom is the fundamental frequency of each note that is present in the recording. And these horizontal lines on top are the harmonics of the sound. And what they realized was that if we try to apply NMF to this spectrogram, for which some of the notes are actually overlapped in time, we can come up with these two matrices here. The one in the bottom left is the basis matrix, which interestingly seems to capture the spectral signature of each note that is present in the recording. So this might be the spectral shape for the D note, this might be for the C note, E, and so on. So this is what is also called a spectral templates matrix. And the other matrix, the H, or encoding matrix, seems to have captured what we call the activations of each component in the left side. So basically it tells us which note is active at which point in time. So this information can be used in order to detect notes, pitches, or more generally to detect the presence of any sort of acoustic components over time, to detect sound events. More or less at the same time when the NMF method was being developed, there was another person called Thomas Hoffmann. And he was working in the field of text retrieval. He was trying to cluster documents, text documents, into various topics. And he came up with this method that he named probabilistic latent semantic indexing, PLSI. This method was adopted by the image and video processing community shortly thereafter, made a few tweaks, and they named it probabilistic latent semantic indexing, PLSA. A few years later, some audio people also appropriated the method, and they called it probabilistic latent component analysis, PLCA. So in fact, all these methods, PLSI, PLSA, PLCA, have been proven to be exactly equivalent to the original NMF method using a specific cost function. However, this probabilistic interpretation that Thomas Hoffmann came up with offers a nice framework that is easy to generalize and extend. So whereas NMF before was mostly rooted in the realm of linear algebra, these PLSA or PLCA methods are more into the realm of probability and statistics, but basically offering exactly the same input, the same output. If we put this in an equation, this is the PLCA model that is frequently used in audio processing. The idea is that we have as input a spectrogram that we call V. It has two dimensions, frequency, omega, and time t. And the basic PLCA model tries to approximate that as a bivariate probability distribution P of omega and t, which in turn can be decomposed into three factors. Firstly, this P of t, which is just a known quantity. This is the energy of the spectrogram. And secondly, two unknown quantities. The first one, this probability of omega given z, is essentially this basis matrix that we had before. This is the probability of encountering a specific frequency template for a specific component z. And the other unknown quantity that PLCA produces is this probability of Z given T, which is the activation. When is a specific component Z or a specific acoustic event Z, when is it active at a given time frame? So this is the second quantity here is something that can be used in order to come up with a system that does, for example, event detection in sounds or pitch detection in music. So in short, PLCA can decompose a spectrogram into a series of spectral bases, these P omega given Z here, that correspond to acoustic events, notes or other types of sounds, and a series of event activations, P, Z given T. And it has quite a few applications in the realm of machine listening. So it could be multi-pitch detection. If we're talking about music, it could be acoustic event detection for everyday sounds. It can also be used for source separation or for source identification if we want to also identify sources. Over the years, also, people have proposed quite a few extensions of the basic NMF model. I'm not going to list everything because it could be too extensive. I will only focus on one extension, which is convolutive models. The idea of a convolutive model is to extract a shifted structure out of non-negative data. Before, the basic NMF model was linear. It was just matrix multiplications. This one is about matrix convolutions. So the idea is, let's assume that you have an image there and you want to detect specific object inside that image, which might be repeated several times. So you want something that can shift throughout the image to locate its position. And this has led to quite a few methods. In the NMF world, this is called NMD, which is non-negative matrix deconvolution. And in the PLCA world, this is called shift invariant probabilistic latent component analysis, SI-PLCA for short. This equation is the basic shift invariant PLCA model for decomposing an audio spectrogram across the frequency dimensions. So again, we have as input a spectrum here. The difference being that this omega here is log frequency instead of linear frequency, and I'm going to explain that later, which is again approximated as a bivariate distribution. And now the output is this spectral template here, which is also now this minus f signifies the shifting across the log frequency axis. And it also produces this two-dimensional probability distribution now given a specific component. This might sound a bit too complex, but if we try to put it in this figure. So here we have what we call a log frequency spectrum of a violin sound, which I'm going to play now. So what you heard is basically like the violin doing a glissando. It vibrates a bit and then goes down again. The nice thing about having as input a log frequency representation is that the spacing between the harmonics of the sound is constant, irrespectively of the pitch. So we could approximate that just by having one pattern, one vertical pattern across the log frequency axis, which is simply shifted vertically in order to account for the difference in the note, in the pitch that's being present. So if we apply this shift invariant PLCA model to this spectrogram using just one component, we get as output this pattern here, which represents sort of the spectral signature of the violin that you just heard. But you can also get this output, this image here as output, which tells you how was this pattern shifted vertically across the log frequency axis. And this actually denotes the pitch. So it tells you that initially the pitch was low and then it went up, it fluctuated. This was the vibrato that you heard before, and then it went down again. So in a nutshell, this convolutive model is quite useful for extracting pitch information from audio signals by taking into account this very interesting property that pitch can be extracted as shift invariance in log frequency representations such as this. We can also do these convolutive models in different ways. So In the previous case, we extracted a one-dimensional template, and the output was, the one we cared about was two-dimensional. But we can also extract two-dimensional patches out of our input signal. So here, we have as input a spectrum of some footstep sounds. You might be able to see the 4 instances of the foot being pressed. And if we try to use one of these convolutive Plca models, but this time to specify that we want our patterns to be two-dimensional, so two-dimensional patches over both frequency and time. And in this case, if we specify that we want 2 components to be extracted by the model, then just by applying this shift invariant Plca method without any supervision, we can automatically extract 2 patches, each patch corresponding to a different foot. And at the same time, we can extract these activations, which tells us that the point over time when each foot is present in the recording. So this also is a way where we can detect acoustic events over time. And these acoustic events might not be just something instantaneous as a time frame, but can be expressed as a spectro-temporal representation. So that was the basics about NMF and how it can be used for audio. I'm now going to talk about a few applications in the realm of music, and then a few applications in the realm of environmental sounds. So for music, something that we proposed in C4DM was to exploit these NMF or Plca methods to come up with a really good transcription system. A system that could transcribe music from multiple instruments. It could also take into account this shift invariance property in order to express tuning changes or vibrati, these frequency modulations that I showed you before with the violin. And could also try to express each note as a sequence of different states. What I mean by that is that if you listen to this piano sound here, I'm going to play that again. You might notice that the sound that you're hearing slightly changes across time. So maybe we could use one template to represent its starting point, which in music we call attack phase. Another part to model its steady state, and another part to model the part where the sound decays in the end. So maybe we can express this piano sound, which is represented here in this log frequency spectrogram, as a collection of 3 spectral templates. And maybe we can also create some links between them, maybe using some Markovian properties like hidden Markov models to constrain the model. And in the end, the model that we came up with was essentially shift invariant Plca, so one of these spectrum factorization models that takes into account the shift invariance property for modeling the frequency modulations and tuning changes, but at the same time with some constraints coming from a hidden Markov model. And at its core, this model will also have a fixed dictionary or a fixed basis matrix, which would contain spectral templates from different notes for different instruments across the entire note range of each instrument. So basically, the model takes as input an audio recording, computes a time frequency representation such as a spectrogram, which is then input to this new Plca model, constrained Plca model, taking as side information this fixed dictionary of note templates. Then the output, which is really a probability distribution of notes over time, is post-processed in order to come up with, in the end, with a MIDI file or any other sort of music notation that can be used. And this is an example of how well the system works. On the top figure here, you see what we call the piano roll representation of a Mozart recording. I'm going to play the recording now. And on the bottom here, you see the output of the algorithm. So this representation is basically pitches, notes, over time. So what you heard is basically that the system was able to capture mostly correctly all the notes, even in cases where you had quite a lot of overlaps. There were, of course, a few missed detections, especially if you have like a dense chord, for example, here. You see here that the upper note is somehow missing. But overall, the system was able to properly capture the core content of this recording, and we were able to synthesize it pretty correctly. Another interesting property of this system is that it can also now, because of the shift invariance property, we can also now display information about the fine-tuning, the sort of high-resolution pitch detection, even if we have overlapping notes. So here's a recording of a string quartet. Etc. But what you can see here, this is the pitch activation output of the system, is that it detects some note events with a slight fluctuations. And these fluctuations exactly indicate this sort of this vibrato that's happening with the bowed string instruments. So essentially what the method does is high resolution multi-pitch detection. And also wanted to show you a small video which sort of delves a bit deeper into the algorithm itself to show how the system actually converges. On the top figure here is the input spectrum. So the inputs to this system. The middle figure here is the approximation. Ideally, in one of these NMF systems, you want to approximate the original input as closely as possible, whilst also having a meaningful solution. And the bottom figure here is the component activation, or the pitch activation, or the matrix H that was presented in the NMF model, so the encoding matrix. And this figure here shows that this is the result of the first iteration, and the NMF algorithm being iterative, it will slowly converge into a meaningful solution. So I'm going to let it run now. So you see that almost immediately, I don't know if it's super clear with the brightness, but by now, this is iteration 20 or so. The spectrum already has been approximated as to more or less match the inputs. And here the, oh, it's finished again, but basically it started showing some of the notes that are present in the original recording quite clearly. So this is basically note index over time. And what I wanted to tell you with this is that if you have a fixed dictionary with these types of methods, these NMF types of methods, you can observe convergence very quickly with 10 or 15 iterations. This system was developed in MATLAB, which is pretty slow, but still the runtime was about 1 to 2.5 real time using a CPU, using a big dictionary of various instruments, orchestral instruments, I think like 23 different instruments. However, given that NMF is mostly consists of matrix multiplications, we can take advantage of the GPU and speed up computations considerably. So there is also an implementation which is at about 0.3 times real time. So in theory, it could be used for real-time applications. Code, by the way, for the system is there, if anyone wants to download it. Yeah, sure.
So the dictionary, how specific is that? You know, is it that particular piano? Is it any piano?
No, actually, I used like a fairly generic dictionary of different pianos, so I always train on different models and test on other models.
Oh, you did?
Yep.
Okay, yes. So of course, with the violins, now with a different dictionary than piano.
Yeah, so basically, I try to have a diverse dictionary, so to have like pitched percussive instruments like piano and guitar, also bowed strings, woodwinds, so to have like a representation of at least classical music, let's say.
Yeah.
And yeah, as far as evaluation is concerned, it's pretty much state of the art, and it's ranked first a couple of times in the MIREX competition. MIREX stands for Multimedia Music Information Retrieval Evaluation Exchange. It's an annual competition in the music informatics world, evaluating systems that can extract information from audio or other music representations. Another thing I wanted to mention before going to the environmental sounds part is that NMF and PLCA can also integrate prior knowledge quite efficiently. This paper that was done with Sidar Siktia, who is not a stranger to audio analytic, I think, was on combining this acoustic NMF type of model with a recurrent neural network that was acting as a language model for the music. So as in speech recognition, which mostly consists of an acoustic part, which tries to understand the audio signal, and the language model, which tries to say that given that the previous 3 words, what's the probability of encountering this word now? We can also come up with a language model for music, so which tells us that given the previous notes were this, what's the probability of coming up with the next set of notes? And because PLCA assumes that the probabilities for each one of these unknown components are multinomial variables, the priors can be represented by Dirichlet distribution, so it's actually a quite elegant solution to integrate any prior information in the model. And more information about the paper, but in a gist, it was shown that by including this music language model within the NMF framework, detection rates for notes and instruments were increased by a vast amount. And finally, before closing off on the music section, just wanted to mention this Silvet note transcription plugin. This is something that came out from my research and was packaged within Sonic Visualizer, which is a Queen Mary software. It's essentially a plugin, a VAM plugin that can work in 2 ways, both in a so-called intensive mode, but also in a live mode, which can be used for real-time applications, and it can do multi-pitch detection. I'll try to show you quickly a demo of how it looks like. So this here is a spectrogram in Sonic Visualizer of, I think, a Mozart piano piece, a Mozart trio, sorry. And Sonic Visualizer has a lot of plugins. This is the Silvet one. Oh, sorry. If you select Silvet, then this window comes up and you can choose which sort of processing mode you want to have and which types of instruments you expect to have in your signal. You have also the option of just having a blind guess about the instruments being present. It runs very quickly, and the result that comes out should look something like this. So basically, these white rectangles correspond to the detected notes. And if you can also play that back, and the results should sound something like this. Oh, sorry. I should click that thing as well. So again, it works quite well. It might miss a few notes, but most of the content is there. And you can download it from the URL there. So moving on to the final part of the talk, which is how these NMF or PLCA methods can be used for analyzing everyday sounds. I'm going to talk about some fairly recent work that was done in the topic of sound event detection or acoustic event detection. The motivation that we had, this is some joint work that was done with Mark Plumbley, was to adapt this PLCA model for detecting overlapping sounds. The scenario we had was office sounds, so sounds in an office environment like door slams, mouse clicks, keyboard typing, people talking, things like that. And the model that we came up with expressed each event class as a collection of exemplars, so example sounds, let's say. So for example, we had like 20 keyboard sounds, 20 door slams, 20 door knocks, and so on. And each of these exemplars was further approximated as a collection of these sound states, the same sound states I showed you before, basically, so denoting the evolution of each sound across time. And these sound states would be controlled again using a hidden Markov model in order to control their appearance. Given that in sound event detection we don't really care about pitch, there's no need to utilize the shift invariance property, and we decided to use this equivalent rectangular bandwidth spectrogram, ERB spectrogram in short, which is essentially an auditory motivated representation. It's kind of like a spectrogram, but it's sampled at specific frequency points which somehow match the perceived frequencies of the human auditory system. It's also quite compact. It's a compact representation, I think like 10% the size of a normal spectrogram, so it can be used more efficiently in real-time applications. So this final equation here, there's going to be no more equations, is the proposed model. It takes as input, again, a spectrogram, V. This is the ERB spectrogram this time. Again, it approximates it as a distribution of frequency and time, which in turn is decomposed into several factors, which are all centered around this dictionary here, a 4-dimensional dictionary of frequency, event class, exemplar ID, I think it's C, and sound state Q. And around that dictionary, there are 3 unknown quantities that are estimated using that model. The first one is this probability of S given T, so the probability of encountering a specific event class across time. So that's the main output that we might want to evaluate in an event detection system. It also has a few other outputs like this probability here, which tells you that given a specific event type at a specific time, what exemplars produce that event? Which combination of exemplars produce that event? So this is a nice property actually of PLCA, is that assuming that we have a collection of, let's say, of door knocks, we can approximate a new door knock sound that we don't have in a dictionary as a combination of the pre-extracted door knock sounds that we have. And the final probability here is the probability given a specific event at a specific time frame, at which state is this event at which sound state? Is it in the beginning of the event, in the middle of the event, or towards the end of the event? And this final bit is actually the one that is controlled by these hidden Markov models. So the top figure here shows the raw output of this event detection system. Basically, it's event class here in the vertical axis over time. This is a probability. This is a non-binary representation. So we need to somehow process it and convert it into a binary representation, which kind of looks like this. I call this event roll. I don't know if you use something similar here, which can be further converted into actually a list of detected events with a start time and end time and a specific ID. This method was evaluated in this DCase data set, which is basically a data set of office sounds in different noise and polyphony or density conditions. And you might observe that the resulting figures are quite low, around 20 or 30%. However, I should note that this is actually quite state-of-the-art, which actually gives an indication of how far we're behind in this field and how much more we can do in order to make systems that actually work. If anyone wants to use the code for this system, which will be presented in this year's ICASP conference, the code is in the URL below there. And a final application for environmental sounds I wanted to mention was that a few years back I decided to participate in one of the ICML competitions, which was on detecting bird species from noisy continuous audio. And I just decided to use a very simple PLCA model, the one I presented in the beginning of this talk, with no fancy temporal constraints or anything more complex than the original model. And still, in a 35 bird class problem with quite noisy real-world recordings, I think they were from a Brazilian rainforest, if I'm not mistaken, the submission still was ranked in the top 25%. So that kind of shows that PLCA was quite able, even in its simplest form, to learn something meaningful from the signal and overcome some maybe more complex methods. I think there were quite a few neural network-based methods that were not able to generalize that well to the noisy test data that the competition had. So to conclude, I hope I was able to convince you that matrix factorization methods are a powerful tool for analyzing audio recordings. I think, for me at least, the main advantage is that they're interpretable. You can make sense of both the input, the output, but also from the in-between parts. So it's as far as from a black box as you can get, basically. And you can inject maybe prior information or some sort of knowledge that can be used to improve your models more. So you can extend the models. Basically, according to the application, you need to create your own model that best matches your sort of intuition, let's say. And they're also quite computationally efficient in the sense that the simple NMF algorithm, the simple supervised algorithm, is basically 2 matrix multiplications over a few iterations. There are quite a few other works that I've done that I didn't have the time to go through, like how to use NMF for recognizing acoustic scenes, to detect percussive sounds, to recognize instruments. But still, the papers are there basically for you to know more about this, and the code mostly. And I would also like to point out that many of these NMF technologies, both from my group but also beyond that, have and are already being used in several commercial tools, as well as in public tools. So as an example, I wanted to show you this digital music lab system, DML in short, which is an online service. You can visit it through this URL here, which enables users to extract features and visualize features in real time from the British Library Sound Archive. And most of these features, like tuning statistics here or pitch histograms here, use as a backend NMF-based methods. So as a small discussion about what I would see in the future in this area. So the first thing that I would point out would be to try and use different representations as inputs. So most of the work being done both in NMF but beyond NMF for analyzing audio is mostly limited to the use of these so-called short-time Fourier transform spectrograms, which is fine, but maybe we can come up with something that's both better in terms of time and frequency resolution, but also faster in the sense that it's a bit more compact. So in the music world, people started using CQT spectrograms, constant Q transform in short, which have some nice properties. More recently, VQT or variable Q transform spectrograms came out. And still, I think there's quite a lot to learn from auditory representations. So representations that are derived from computational models of the human auditory system. So taking into account the fact that people process sounds in different time scales, as well as in frequency. So this figure here shows an example of this is a CQT spectrogram here, and this is a VQT spectrogram here of I think both cases a piano sound, both of which are low frequency representations. Another interesting direction I would point out would be the use of language models in analyzing everyday sounds. So this is something I don't think that really has been touched upon, but basically, let's assume that you want to come up with a system that detects various office sounds. This is an event role representation. Again, this red event might be keyboard typing. And these blue events here might be footsteps. So you see that sort of there's a difference in the sense of the duration, the expected duration of each event, but also on the frequency that each event might be repeated. So maybe we could come up with a language model that actually tries to incorporate that knowledge that we have and not just rely on the raw audio. Another thing that we still have to do is to come up with a good taxonomy, which is not really there yet, although a few people from NYU, I think, are trying at least to come up with a taxonomy for urban sounds. And the final thing that might be more applicable just to NMF types of approaches, but also beyond that, is to, assuming that we have a method that uses a dictionary of some sounds, and then a sound from the same class comes up, but it sounds different because maybe the room is different, maybe the microphone is different, maybe the source is different slightly. So we need to come up with methods that can adapt to new conditions, either recording conditions, room conditions, or source conditions. And that's it. Just before I conclude, a few announcements. The first one would be this IEEE challenge on detection and classification of acoustic scenes and events. This is the second iteration of international competition on sound recognition. We have 4 tasks: scene classification, 2 event detection tasks, and an audio tagging task. I'm involved in the one of the event detection tasks in detecting overlapping events. And if you want to participate, basically submitting your system to some hidden data. And if you want to participate in the final workshop for this challenge, which will take place in the UCIPCO conference in September, the deadline to participate is, to confirm your participation is 31st of March. That's item number 1. Item number 2 is that in case you're interested in the topic of sound recognition, there's going to be a special session co-organized by Mark Plumpley, Thomas Virtanen, and myself at the ICASP conference about a month from now. And final thing, we're hiring. So if anyone knows someone who's interested in machine listening, there's a deadline for a PhD at the Center for Digital Music in about a week from now. And thank you again for listening. Thanks to all these people who are somehow involved in this work and to the funding bodies. Thanks very much.